Today's episode is called Orchestrator-Workers, Evaluator-Optimizer, the hinge, where the model starts deciding what work exists. So, last episode we ended on parallelization. So you have your invoice, it's read, you write the subtasks yourself, you have the check amount, check vendor, check policy, and they fan out together. So it works precisely because you knew all three and you wrote the code and you have these steps. It's like it's a workflow basically. And they are basically same three branches, every single run. The issue happens when you have a 40-page consolidated statement. You have 61 line items, 9 different POs, 3 currencies. With these numbers, they can vary, of course. So how many subtasks are you going to write in that case? How many, for this use case, how many subtasks does this document need? If you go about it and you try to code it deterministically to find how many of these tasks exist, then it might never end, and you cannot predict it by hand. It's impossible. It cannot be enumerated. So the subtask list depends on the input, which means it can only be written after something reads the input. Something has to decide it at runtime. And there is one component in your system that already has read the document, which is the model that read the invoice. So what you do is basically you let that model that read the invoices just decide how many of these tasks you're gonna have. And that's the pattern orchestrator and workers. So Anthropic's definition is word for word. A central LLM that dynamically breaks down tasks, delegates them to workers. The workers are themselves LLMs, and synthesizes their results. So you have 3 moving parts. You first break down, delegate, then synthesize. Let's look how this looks like. So you have here the document, you feed it to the orchestrator, and what comes back is basically a list. The amount of items that you have in this list is going to be variable. It could, so for example, here the document happened to have 3 purchase orders with different line counts, and there is also the issue of currency here. And what you do is basically you hand it a different statement, and the list comes back a different length. So that's not what you do, that's what would happen in reality. From there, you delegate. So your code walks that list and spawns 1 worker per item. Here it's dashed because you could have more workers or you could have less workers. The number of workers does not exist when you write the code. It's whatever this orchestrator said. It's whatever this list said. So that's the point of this. And then the workers do the work, and then you have a synthesizer. Orchestrate, you have an orchestration, work, synthesize. That's the pattern. And Anthropic's guidance on when to reach out for it is exactly our situation here. Or verbatim, it's complex tasks where you can't predict the subtasks needed. They have another example, which is coding, and the number of files that need to change depends on the task. So yeah, if you code, you don't know how many changes you're gonna have if you're adding a feature or removing it, so you'd have an orchestrator that does that for you. So this is what it actually looks like, and it's worth seeing because it's so much less exotic than what it sounds. A orchestrator function calls the model and returns a list of sections. So you have here, that's what it does in pseudocode. Then you have the assignment part, and then the synthesization, which is pretty simple here. And every line is called ordinary code that you wrote. The shape, orchestrate, then work, then synthesize is fixed. It never varies. But what happens after that is what varies. So the only thing that is unknown until runtime is the length of the list that will be produced here. So here. And actually LangGraph names the mechanism directly. It's the send API quote the send API lets you dynamically create worker nodes and send them specific inputs. So each worker gets its own state and the outputs land in a shared key. The orchestrator can read in the end. So hold on to that. You have a fixed program with the variable length list in the middle. The whole argument of this episode lives in that one system. So you just need to remember that image of a varying list in the middle, and you don't need to remember anything else. So I just wanted to remind you of one difference between the router and orchestrator. So in the last episode, we have spoken how the router is taking one of these paths. The orchestrator is having a variable list of paths. So that's the only difference. The router selects and the orchestrator actually invents. And it's actually a bigger step than what it looks like. So in previous videos, we have been talking about the difference between a workflow and an agentic system. And here, the definition for workflow is the predefined code paths. And here you tell me, Aziz, but that's a problem because the subtasks are not predefined. You have a central LLM dynamically breaking down the tasks. And that's the debate of a previous video that I've been talking about, is it's not the boundary between agentic and the workflow is actually not very clear here. Because in a way, you have the predefined orchestrate, then do the work, then synthesize, and that's predefined. And also the subtasking is not predefined. So which one is it? We don't know actually. So the boundary is a bit confusing here. And I will tell you, Anthropic put it in workflow. So you just put it in workflow as a pattern. The debate is not the point of this. The second pattern Anthropic names is one LLM call that generates the response while another provides the evaluation. So this is what it looks like. You have the generator, you have the evaluation. Each one has their own role, and the generator writes a draft. And from there, for example, if the evaluator says, hey, there is an issue here, it sends it back, tells you, hey, for example, total ignores the credit line. It tells it to draft the second part. So you're creating a loop, and like you go in, out, until the evaluator is happy. And then it passes and tells you accept it. So the idea here is the same as humans would work, or you would have a professor or someone evaluating your work, and you are a student, for example, and it's like drafting, critique, redraft. And when to use is it works when there are clear evaluation criteria, when a human articulating feedback would demonstrably improve the output, and when the LLM can provide that feedback. Now, the last clause is doing far more work than it appears to, like when the LLM can provide that feedback. B12 is all about it. We will talk about that ahead. Now, the research version, and this is called self-refine. It was from Madan and colleagues in New RPS 2023, and their twist is that both roles are the same model. So basically, it's one model that's going to do these three tasks. A generator, the LLM providing the critique, and the refiner. 3 prompts, no extra training, no supervised data, no reinforcement learning, nothing. And it got 20%, basically an average of 20% improvement. But the issue is that there was an improvement on the dialogue responses. It went from 25% to 74%. On code optimization, also there was an improvement on average task performance. In math reasoning, the authors call the improvements modest. So the average is hiding something here, is that on taste tasks, so even if code optimization, it's like, yeah, sometimes it's taste tasks, sometimes it's not, but basically on taste tasks, it has huge effects. On reasoning, not really. There you don't really have huge results. And the authors trace the math results to the model's inability to accurately identify whether there is any error. So, which is generally the perfect setup for the next slide. So there was a paper from Huang and colleagues at Google DeepMind. It was submitted to ICLR 2024, and the title of the finding is LLMs cannot self-correct reasoning yet. So LLMs struggle to self-correct their responses without external feedback, and at times their performance actually even degrades after self-correction. So you're actually, with the loop, you're making things worse. So they give this failure a name. It's intrinsic self-correction. The model basically endeavors to rectify its initial responses based solely on its inherent capabilities without the crutch of external feedback. In plain terms, it rereads its own work and nothing new enters the system. And that's the whole mechanism. No new information arrived. The grader has exactly the same blind spot as the writer. It missed the error while writing, and it misses it again while grading. That's not a prompting problem you could fix with a better critique prompt. There is simply nothing new to correct against. Now, the other case, the evaluator is a compiler, or a test suite, or a schema check, or a database lookup, or even a tool result, something outside the model. And now, a fact the model did not have arrives in that loop, and the refinement has something real to refine on, basically. So, and this critique was made in SELR 2024 by the same authors, and they say it plainly. They say plainly that there is a huge, crucial importance of external feedback to our loop. And so here we created a rule, and it's the one thing to take from this whole episode, the second half, and when we are talking about the second pattern. The loop pays exactly when the evaluator knows something the generator doesn't. If it doesn't, you're paying for 2 calls to be told not everything looks good. So how this would look like, for example, for our accounts payable example that we have already spoken about in this full series, is that you would have the following gate. So you have the extraction, and then you'd have the following gate to sort of grade what you extracted, or like the draft that was done by the first extractor. So it's basically schema validation. You'd have the three-way match against the purchase order and the goods receipt, and the arithmetic. Does the total equal the sum of lines minus credit? So that's your evaluator. And then from here, you refine with error. So I actually took a bad example here on purpose on why you shouldn't use AP for such a with such an architecture, is because actually, if you look here, first, the benefits plateau after first refinement, so you don't need to refine to do the iteration. Second, with the more rounds you're adding, it scales serially. So like you would be having for n rounds, you'd have two n plus 1 calls. So, and you can't parallelize them, or you need to wait for one to start another. And there is one thing that I learned personally from all of this, is that this pattern would work best in use cases or tasks that are very subjective, and even with the external validation. So even with the external validation, you would still have something that is subjective, but you add something like an external affirmation, an external check, and that would create actually a better loop. So one of the issues we have been seeing is that in production this pattern often breaks, because the lenient evaluator, which is here the self-refined documents, when they are confronted to their own results, for example, ChatGPT's feedback would often says that everything looks good and this was at 94% of math instances. So an evaluator almost is not objecting to its own assessment, and you're paying for paying for the call without getting anything meaningful most of the time for it. Actually, and they counted this in this paper by Zhang and colleagues in NeurIPS 2023, and ChatGPT favors its own assessment 10% more, and Claude 25% more. So is it correlation, is it causation? But the numbers are there, and I believe that there is. So would this mean that Claude is better or ChatGPT is better, but that's another question to ask. But generally, if the model is judging itself, it is favoring its own answer. Third, oscillation. It keeps, and this is the thing that you need to understand, is that it keeps editing and never converges. Every framework ships the same break. So Google, for Google's ADK, gives you a loop agent with max iterations, meaning that you can exit early when certain quality threshold is met. You can exit if you meet the max iterations, just like any loop, in programming. On the other side, you have LangGraph, which loops until acceptable. So you set both the quality bar and the hard ceiling, and from there you would find what you want. Last part is Evaluator-Optimizer is different from the reflection. So there is this pattern, sub-pattern, I would say, because Evaluator and Optimizer is two fixed roles inside the loop you wrote. Reflection, which is coming from Shin and colleagues, is the agent verbally reflecting on task feedback. So every time you get task feedback, it would take a snippet or the meaning of that, and it would store those reflections in episodic memory. And retrying inside, and it would retry into its own inside loop with those learnings. So one is basically like a building or like a scaffolding around what you have. The other is its own loop, its own agent. So that was it for today's episode. It was quite long, so these are the themes we went through. If you like the content, please like and subscribe and follow me on LinkedIn. Thank you.